Koutou katoa. Welcome along to our annual Fresh Off the Ice series for 2022, hosted by the Antarctic Society of New Zealand and the Wellington branch, and supported by the Antarctic Research Centre and Victoria University. It's been a really busy season. I was lucky enough to go along to the Antarctic Science Platform kind of recap, and this is going to be a bit of a taster really, but there was actually so much going on that I think we might end up having a second talk. I know that there was, quite a few other people involved in work down on the ice that wasn't necessarily New Zealand driven, and it's always such a pleasure. This is one of my favourite talks to speak to and host. So tonight we've got Natalie Robinson, who is on the Wellington Branch Committee. She'll be talking about platelet ice and collecting that. And we have Francesca speaking on behalf of Alana and Alex, who is our first Victoria University all-woman team down to the ice. And followed up by Linda and Sam, who are master's students that were involved in the CAM ice stream. Should the 200% success. And we'll finish up with Jamie Stutz, who's also on the Antarctic Society Wellington branch, and his experience on the RV Aron. So we'll just get started. I should say Natalie has to nip off at it before 7. So if you have questions for her, then you should ask those immediately after her talk. Thank you.
Cool, thanks Georgia, and thanks to the Antarctic Society for giving me a little bit of time to share our season from this year. Just short introduction, I'm a physical oceanographer working at NIWA, but this is a project that has come out of the Antarctic Science Platform and is a collaboration between quite a number of institutes. So what you are looking at there in this title image is we're down in the ocean looking back up towards the surface, and so the light that's coming down to us has been filtered by a layer of snow and then solid sea ice, and then underneath the sea ice is this layer, quite a unique habitat or quite a unique structure of individual ice crystals. They're called platelet ice crystals, and they've floated up to land against the base of the sea ice. So in this case, you're actually looking through about 4 meters of these layers that have built up. You can imagine them like autumn leaves that have just floated, but they're going the wrong way. But we've seen them under first year ice in excess of 6 and sometimes 10 meters thick. So just a wee bit of explanation as to how they occur. So we have the ice shelf, which is the glacial ice that's come off the continent. And so that forms an ocean cavity. So just to give you an idea, the Ross Ice Shelf, that's sort of the order of 500 kilometers long. So you've got quite a decent piece of ocean that's covered by ice. So the relatively warm ocean water can get in and will get all the way to the back where it can start to melt the ice shelf, even though it's very cold. It's got enough energy to start melting. And then that water, because it's now got a component of fresh water, it wants to rise. So it has this tendency to flow out towards the open ocean, basically tracing the bottom of the ice shelf. And as it does so, there's a quirk in the freezing temperature that means that although it doesn't actually change its temperature and salinity properties, the water, because it's now under significantly less pressure, finds itself colder than the local freezing point by the time it's released at the front of the ice shelf. So this is called supercooled water. It's water that's actually below its own freezing temperature. and yet it's able to remain liquid. So it's quite an interesting phenomenon. And of course, this is water that wants to freeze. It's just waiting for an opportunity. It needs ice crystals to freeze onto. So we come in right at the front of the ice shelf where we can get through the sea ice and to access this water. So to give you a bit of an idea, here's two contrasting images of McMurdo Sound, one in February and one in October. And for your reference point, here's Scott Base at the end of Ross Island. And this red line here denotes the approximate front of the ice shelf. So to the north of the ice shelf, we have in February open water, but in October, when we come down at the end of the winter season, that open water has frozen into sea ice. So we've got this platform that we can drive out onto. And of course, with Scott Base's location there, we're right at the intersection between these two types of ice. So what I've been studying for, well, at least a decade now, is this flow of ice shelf water that comes out from underneath the Ross Ice Shelf and flows along the Victoria Land coast there. So this latest season, we went down in October last year, and there were 5 of us on the ice. Greg Leonard from Otago University, Ken Ryan is here at Victoria, Steve Parker was at NIWA, and Brett is also at NIWA with me. But we had an important 6th member of our team. You can see the phone in Steve's hand. We were talking to Craig Stewart, who designed the piece of equipment that I'm going to introduce you to. And of course, he left us a few niggles to sort out on the ice. So here we are having a conversation at the end of the day, just going back and forth about what might be going wrong. So to give you just a little introduction about what this stuff looks like, this first frame that you're looking at is basically solid sea ice, but we're going to move down beneath the sea ice, and you can see this layer of crystals that has accumulated. So, I've done this several times. So in this case, the layer of platelet ice is about 2 meters deep. And now we're looking side on right at the base of the sea ice and the top of the platelet layer. So you can see there's kind of solid sea ice at the top, and then we've got all these individual crystals underneath it. In this case, you can see this beautiful crystal clear color. But then if we move, now this was only 50 to 100 meters away. So again, you're looking at the intersection between the base of the sea ice and the top of the platelet layer. And here you can see it's completely swamped with algae that have colonized it. So on quite small scales, we're getting very different biological association with this platelet layer. You can imagine that because you've got this fairly robust structure, it represents quite a protective habitat, and there's also lots of surface area for everything to attach to. So actually there's more primary productivity associated with platelet ice than with any other type of ice in the ocean. And also platelet ice is known to be a silverfish nursery. So the aspiration for this project was basically to look at all of the biology that's associated with platelet layer, with the ultimate goal of trying to predict knock-on effects of various climate scenarios for the Ross Sea ecosystem. So the engineering challenge we set was to try and core this delicate platelet layer structure with some various requirements. But the issues that we face, of course, that we're working in supercooled water, which wants to freeze onto anything and everything. We're having to work blind, basically 6 meters beneath our feet. But we're also concerned about maintaining hydrostatic balance. And I'll just quickly explain what I mean by that. So here we've got this multi-layered structure. And what we want to do is collect a sample like this. But as soon as we start to lift the sea ice, the solid sea ice core, and the platelet ice comes with it, we've disrupted the hydrostatic balance. So the ocean will want to flow up and flood that platelet ice. And of course, we don't want that to do that because we need to keep the ice and the water together. So the system that we've come up with, this is the easiest way to image it. So we've basically got a big long drilling core barrel, and attached to the top is our off-the-shelf Hilti drill. So what I thought I'd do is quickly step through the various parts of the procedure to collect a sample. So the first step is just using a standard Jiffy drill to drill a pilot hole. And then this is one way that we tried to overcome the problem of hydrostatic balance. So now we're drilling across our sample hole at a 45-degree angle. I'm going to drill all the way through into the ocean. And just have a quick look at what that looks. So now we're looking straight down the hole. Kovacs drill coming in from the side. And it took a few extensions of that to actually reach the ocean. So finally, with this one, we broke through and into the ocean. So the water just started leaking a little bit, but it's just because the drill was still in the hole. It was difficult to tell what was happening. But as soon as we pulled it out, flooded to fill that void that was created. Okay, so carrying on, now we've got a hole that's full of water. That gives us opportunity to clear the ice chips because they'll float, so we can scoop them off at the top and continue drilling, but this time we're drilling a wider hole to allow our drill system, our sampling system to fit through. So quite a bit of sieving of ice chips and frazzle ice off the top. And then we set our base plate into position and attach the rack and pinion that's going to hold the drill. Now we've already got most of the way through the sea ice with that Jiffy drilling. So we're just placing the core barrel into the hole, and then we're going to attach the drill to the top of that core barrel. And then the actual drilling part is about 0.5 metre of sea ice. So just looking at that in real time, what Steve's doing here is he's just gently lowering the head of the core, the cutting part, until it strikes the bottom of the hole that we've already made. Then he spins it up to full speed. And so now we're actually drilling that last piece of sea ice down before we hit the platelet ice. And we've got a stopper on so that it won't cut further and into the platelet ice. But you can see it's quite happily just eating its way through the remaining part of the sea ice. It's a really lovely piece of equipment. It's really worked out really well. Okay, and then take away the drill and the rack, and we're going to replace that now with an extension of the core barrel. So now we've got enough continuous core to get all the way through the sea ice and then the platelet ice and into the ocean underneath it. And then we're going to plunge through, because we're now plunging through the platelet ice itself. And you can sort of think of this as like an apple corer. Did you see it go? So I'll slow that down into real time. 3, 2, 1.
It went in the water.
And here it is from underneath. Is it playing? Is it playing? So we've got to the point now where inside that barrel is isolated the sample that we want to retrieve. And so we've got a couple of ways by which we can actually get it out. One, this is quite a complicated way, but it was sure to work one way or another, required drilling a second hole and then deploying this whole separate piece of apparatus through it. So the first thing that came through was a water pump, and then the next piece of frame has in it an inflatable plug. So now we're manipulating that last piece of frame by turning a winch from the surface to draw that arm up to its nearly horizontal. Now this we couldn't do without this underwater view. We have to have someone constantly watching the underwater camera and giving directions, turn right, turn left, up a bit, left a bit, you know. So what I'm showing you here is a 3-minute summation of a process that actually took us over an hour and a half. Well, you can sort of see what's going to happen. Maybe I'll just skip forward a bit in the interests of time. Inflate the bung and then send it up into the bottom of the tube. And then once it's in there, we'll inflate it further so that it actually seals the bottom of the tube. And then we turn on the water pump, which is going to pump water from the ocean directly through the pump itself and into the core barrel, so that it's adding water pressure and forcing what's actually our sample further up where we can collect it at the surface. And then reverse the whole process to get it out again.
This is a girl from Niwa. They're taking samples out of the Flecknoton and stuff, and how they went about it and stuff. It's interesting. Yeah.
Okay, just hang on. Sorry. Would you mind muting your? Would you mind muting your microphone there, please? Anyway, I'll carry on. So once we've got that sample coming up, we've got this sampling unit that goes on the surface, which will actually collect the sample with.
Not coming out.
But the other method of actually extracting the sample is to just apply a vacuum on the surface and draw it up. And so you can see that would be a whole lot less fiddly way to do it, because it only requires one hole and not all this underwater fiddling around business. But we weren't certain ahead of time that this would work. So you can imagine how excited we were to actually get this going. And now you can see the Frazzle crystals coming in and coming up.
You think that's one bubble source or two? I think that's the one there.
Oh, is that where it is? Sorry. Thanks. Sorry. Okay. Carry on. No, we've done that one. And so here's a close-up video, which is quite exciting, because what it's showing is that we've done all this stuff to isolate our sample, and now we're sucking it up. But the actual structure of the platelet ice is what we would expect. We're fairly confident that it's had minimal disruption, which is really exciting, because it means we can have higher and higher resolution for our ultimate samples. And then the last stage, so for the purpose of testing this system, which is what we've done this last season, we wanted to get to this point. So we'll have a more sophisticated version of this when we're actually sampling for science. But the thing is, then we've got a knife gate slide across these two plates, form a knife gate, which both holds the vacuum in the lower part of the tube and separates the the sample part that we're going to siphon off here or tip off here. So you can see we can keep doing that in sequential sections of the entire core. And I just wanted to show you one more quite exciting wee one. So again, we've isolated our sample and now we're ready to suck it up into the sampler. And this one gives you quite a good example of just how undisrupted the sample is. So what you're looking at now, there's a wee brush, and then there's a part is the core of sea ice, but then immediately under that dark stuff is the algae that's in the top part of the platelet layer. You can actually see there's two distinct layers of algae there. And so they're about 20 centimetres separated. So I mean, it's lovely, it's so well preserved. So that's all I wanted to show you tonight. I've got QR codes there just in case you're interested in another couple of videos about this. But over the next few months, we'll be modifying this system so that it's going to be as efficient and fast as possible. And then we've got 2 more seasons planned, hopefully this coming season, one in Southern McMurdo Sound and then in Terra Nova Bay as well. And there's a lot of people involved in this development, as well as funding from 3 different sources. So thanks very much.
That was amazing. Have we got questions from the room or online? Stefan?
What's how's the signal, like the cell phone signal?
Oh, we were using an Iridium, and it was okay. It was pretty good. The email with it was slow, but an actual phone conversation was fine. Maybe a bit dodgy, but you know, in terms of the speed and everything, it was fine.
And how long, like from idea to deployment, was the process of making this super tool?
I would say we actually spent about a year discussing and trying to establish the design criteria, because there's lots of people with different, you know, ultimate what they really want from this, but some of those were incompatible. So there was all a bit of, as well as, you know, Craig, who did the design, and there's some others of us who are very familiar with the environment, and we were trying to relay what was possible and what wasn't. So it did take quite a while to actually establish the baseline. And then I think Craig spent another 12 months designing and getting the custom pieces built. So we were glad to finally get everything together. It didn't actually ultimately all come together until we were at Scott Base. So just with the delays with lockdowns and COVID and things. So yeah.
Another one?
Sure.
This thing scalable, like can you do bigger layers as well, like 10 meter?
Well, of course you can. In terms of this setup, you're limited by the actual space that the drill gives you, but you could manipulate that. But you're going to have, so this is one of the things we discussed. Obviously, a huge sample would be awesome, and then we'd get heaps of information. But you're actually going to have to handle that somehow. So in this case, you know, that 1 meter with a 25 centimeter circumference, and even if you're only filling it halfway, that's quite a weight of sample to manage. So you just have to trade all these things off in terms of how much sample do you actually need to get, and we're pretty confident now that we've seen how undisturbed this is, that size is going to do the job for us. Yeah.
Is there any way to keep the stratigraphy kind of intact on that, you know, when you put knife gate through?
So we know at that point that it is, and we've been debating. So there's some ideas floating around as to what we could do from that point on. We could freeze it in place, but that's going to be problematic for the biology, because as soon as you do that, you're actually getting phase change, and so the salt content of the liquid part will go up, and so that's going to affect the actual biology.
Right.
So we could do that, but we think in terms of the science that we're trying to get out of it, it's better to separate the ice and water at the point of sampling it, and then we know what's come from where, and we haven't minimized at least how much we've changed anything.
Yeah. Oh, well, that's fantastic. I think we can all agree that's a beautiful advancement of technology. And yeah, can't wait to see what the results look like.
Cool, thank you very much.
I have ejected your.
Oh, you have? Okay,
Yeah.
I'll take that. Sweet.
Thank you. Okay, up next we have Francesca. Am I still screen sharing? No. I think it's good.
So hi everyone. So I'm going to talk about the K865 event, where we were looking at the velocities of the Ross Ice Shelf. Me, Alana, and Alex, we went there in November and December of 2021. So, So why were we looking at the velocities of the Ross Ice Shelf? So it's really important to understand how the ice shelf is responding to changes in climate, especially over different timescales. So we have short timescales, which involve seasonal changes, such as changes in sea ice, which promotes changes in the velocities through enhancing basal melting or reducing basal melting. But we also have longer term changes, such as anthropogenic climate change inducing the warming of the atmosphere and the ocean over yearly or interannual timescales. So by observing the velocities of the ice shelf, we'll be able to understand how the velocities are changing and if they're changing on short or long timescales. We've got a huge range of satellites currently tracking and capturing the velocity rates of the Ross Ice Shelf currently. However, they're unable to capture seasonal changes that the GPS units can. And we also have tidal changes that these satellites are unable to capture. So GPS units are really important to be able to capture these short changes in velocities, but also validate the satellite products that we have. And more importantly, they're really good to be used to improve our ice sheet modeling projections. These are the projections that we're providing to the governments to tell them, look, we're telling you how much Antarctica is melting and why. So to be able to make these projections even better, we need ground data such as GPS units to tell us what's actually happening on these shorter and longer timescales. So our project our aims were to provide like a near continuous observation of the flow rates of the Ross Ice Shelf, especially the Western Ross Ice Shelf. We've had previous papers showing that the Western Ross Ice Shelf has experienced increased basal melting, and we don't know how the velocities are responding in this area. So by providing this near continuous data set, we're hoping to be able to answer how is this ice shelf responding to changes in climate. So to do that, we visited 2 existing sites to collect GPS data, and we also installed 4 new GPS units across the Western Ross Ice Shelf. So here we have some maps showing you the sites. So on the left-hand side, we have the 6 sites, and you can see that they're going out from the Western Ross Ice Shelf towards the middle of the Ross Ice Shelf. And we can see that the closest sites are like less than 100 kilometers from Scott Base, but the furthest away sites are about 300 kilometers. And then on the right, we've got some satellite observations of the velocities. And we can see there's 2 red dots. The 2 red dots are the sites that we already installed in the previous season before COVID. And these are the sites that we're going out to collect existing data. And then the 4 black dots are the sites that we went to go out to install some new GPS units. And from this velocity data set, we can see that there's changes in the velocities even between these sites. And so it was very exciting to go out, especially to the middle of the Ross Ice Shelf here, to see what was happening, because we've got some previous data sets here showing that the velocities are increasing substantially. So now that I've sort of explained, the science why we're doing it, I thought I'd introduce the team a little bit more. So we were the first all-female team from Victoria University, which is very exciting. We have Alana, who is the boss of our team. She's a PhD student currently about to hand in, which is why she's not here. Then we have Alex, who is here in the crowd, and she's a postdoc with the ARC Modeling Hub. And then we have me, Fran, and I'm also a PhD student. So for me and Alex, this is our first time going to the ice. So I'm sort of going to give you our experience. There's going to be lots of photos of seals and how we felt about landing in Antarctica for the first time. And I also talk about the science. So before we actually went to Antarctica, we had to buy all the equipment, tailor the equipment for our field work and ship up to Scott Base. And then we had a lovely 2-week isolation in Methven, where we met some friendly sheep. As you can see, Alex here is enjoying the company of the sheep. And we stayed there for 2 weeks, I think a little bit longer because of flight delays. But finally, we got to Antarctica, which was very exciting. We had a very cramped, noisy journey on the plane. And then we landed on the ice and we got into the Haglunds to Scott Base. So once we got to Scott Base, we settled in and we were able to have a couple of days where we could go and see the Weddell seals on the sea ice before the sea ice started to break up, which was really fun. During this time, Alana prepared our cage, which is where we had all our equipment and where we could set up all our stuff. And me and Alex did some field training, which meant we got to go out onto the ice and spend a night there, which was really cool. So now I'll talk about our actual field work. So first of all, we had to collect the current GPS data that was already out there. So those were the 2 red sites from the previous map. So to do this, we had to take a plane, a Twin Otter, out to the sites. And it was quite nerve-wracking because we had to provide estimates of where these GPS sites will have moved over the 2 years that they've just been there. And from the plane, we had to detect our green flags, to be like, oh yeah, that's our site. And then the pilot had to go around and land on them. So that was really exciting. So we landed and it was like the relief was amazing that they were actually still there. And the solar panels were still standing up and the antenna was still there. So then we just started digging and we dug and we dug and we dug until we got our big box and we opened our big box and it was like the GPS unit's still recording. So it was very exciting, especially for Alana who went out the years before. So once we got to the GPS sites, we downloaded the data and then we moved the sites slightly up above the snow so that we didn't have like more meters of digging than we want to for the following year to collect the data. So these GPS sites are still recording data and they were able to record the last 2 years of data, which is fantastic. And I'll show you some of the results later on. So the next part of here's the before and after. So you can see Alana standing, how far the solar panels are deep into the snow, and then afterwards. So it was a lot of digging, which I think is what Antarctica fieldwork is all about. So next we were installing the GPS units. So for this, from my previous map, you could see that the GPS units were quite far out on the ice. So we had to have a really good weather window for this. And we'd been told, me and Alex, before we got there, that you're never going to get out to these GPS sites. But luckily the weather gods favored us this year and we were able to get out to all of our GPS sites and install new units, which was really cool. So the flights over were spectacular as always. And the pilot was even excited to go somewhere new that she'd never landed before. So for installing the GPS units, yeah, again, more digging. We compiled the solar panels and the antenna and all the cables. We put our box in and we put our batteries in. And then that resulted in us having 4 new sites that is currently collecting data on the Ross Ice Shelf in the Western region. So this is really exciting that we have 2 years of data already, but we're also going to have another year on top of that and then more years of data that we're going to be able to build up a complete understanding and map of these changes in the Western Ross Ice Shelf of the velocities. So I've got some initial results. So GPS units record positions, and from these positions, we can record changes in velocities. So there was a map here, but it's gone. But wait, I'll go back to I'll show you which one's site. So site 1 is this one closer to Scott Base, and site 2 is the one closer to the Calvin Front when we look at the results. So we can see that site 1, the velocity magnitudes are actually smaller compared to site 2. I'm currently assuming this is because site 2 is closer to the Calvin Front, so it's experiencing maybe enhanced basal melting or changes seasonally, such as changes in sea ice, changes in oceanic conditions. And we can also see here that we've got some gaps in the data. So this is because again, we are assuming that in the winter months, there was some freezing ice or snow on the solar panels, which resulted in them not being able to capture, to power the GPS units to capture the positions. We can see that there's not a huge amount of seasonal change. The velocities are changing very small between the days, but we can see Site 2 that there's slightly higher velocities in the winter months, which has also been found by previous GPS units that have been observing the Ross Ice Shelf. So it was a very successful season for our team. We managed to get out to all our sites, and we're hoping that this GPS data over the years, I think we've got a couple more years to build up, we'll be able to validate satellites and also be able to improve our model results that we have. So hopefully we go back out and collect more data. Maybe they won't let us and tell us not, wait another 2 years and then go back out. But we'll just see. So thanks for listening. That's it.
Do we have any quick questions, or are there any online? Just from Jamie saying congrats team. Okay, well, please put in any questions throughout the talks as well, and we'll come back to them. What am I doing? Okay, and now we have Linda and Sam. Oh wait, I had a question. I've just forgotten. I'll go back to your slide. What's the higher frequency variability in that, like on the month? Is it tidal?
Yeah, we're thinking of these like frequency. But again, just very initial.
Beautiful. Yeah. Okay. Yeah. That's good. I'm just gonna put that
on. All right, so we're gonna be talking about what we did this summer at ChemIStream 2. And it was a multidisciplinary investigation of the subglacial channel that's located there. That included surface geophysics, as well as oceanography, sedimentology, and some surveying by the University of Otago. So this is us. We both came down here, we came down to Antarctica on summer research scholarships. I was working with Gavin Dunbar on the sedimentology, so we were attempting to collect sediment cores from underneath the ice. And
I was working with Hugh Hogan on the ground surface geophysics down there.
And I'm a master's student, so the data that's collected from here I will write my thesis on that, and Sam will do his honors and his master's on the data that was collected. So before we start talking too much jargon, I wanted to quickly introduce, for those who don't know, the difference between an ice sheet and an ice shelf. So the ice sheet is ice that is grounded to the underlying rock. Ice shelves are the floating equivalents of that. So there's a water cavity underneath it. And then for a little bit of an introduction on ice streams. So we went to the ChemIStream. The Ross Ice Shelf has a total of 6 ice streams feeding into it. They are together responsible for 30 to 40% of the ice loss from the West Antarctic ice sheet. So they're really important for ice sheet mass balance, and the ChemIStream in particular, because it stagnated around 160 years ago, is of particular interest because it's thought that this contributed to the positive mass balance of the Ross Ice Shelf at the moment. So ice streams flow faster than the ice that is located right next to it. That's due to a lot of factors, but most of it is the underlying geology. So we went over here to KISS 2 just for a little orientation. Scott Base is right here where the dot is. So we went about 1,000 kilometers away from Scott Base. We flew out to the Disciple Coast over here. KISS 2 was about 50 kilometers away from KISS 1, where a science team went in the 2019-2020 season as well. So why did we choose, or why was KISS2 chosen? It's because it's located at the intersection between an under ice shelf river and it's where it enters the ocean. So like a normal world equivalent would be an estuary where just the river enters the ocean. But what makes KISS2 so special is because these locations have actually never been physically investigated. So it's very excited to have been a part of this. So the overall science objective was to explore Antarctica's hidden under ice rivers and their role in future sea level rise. And so we had 2 oceanography teams. One was a team from NIWA, and we had an American team from Georgia Tech that had a robotic oceanographer. The team's called IceFin. Then it's Gavin and myself for sedimentology. It's Hugh and Sam for surface geophysics, and then Holly Still from University of Otago doing surveying to look at the flexure of the ice shelf with the tides.
Cool. So here's a of the camp. So you can see on the right there, we've got the mess tent, and on the left, you've got us coming to land, and you can see all the camp set up. And on the right hand side, you've got all the berms where they stored all the fuel over the winter. So at the camp, we had the rec tent, which we're allowed to use with the Scott-based staff, as well as our own personal tents and a couple of science tents for cold storage and a warm storage tent, which we usually manage to use to do science in. So I'll give you a little rundown of the surface geophysics that took place at KISS2 last summer. So this is a little map of the KISS2 area, and you can see the grey dots are the 15 passive seismometers that we installed for 4 weeks. They were continuously recording, and that data set's going to be used to measure a whole lot of things, but ideally it's going to be here to kind of sound the flow through the river channel. And the orange lines are 50 kilometers of profiling radar that I undertook. We're down there to get a high resolution image of the channel. I also undertook some common midpoint radar measurements that were used to better constrain the velocities through the firn layers, the surface. So I've got a video here of us retrieving one of the passive seismometers that we installed. So they're buried about 1.5 meters below the ice with a battery that managed to last the 4 weeks, which is pretty cool. Here's a high density ground penetrating radar array that Craig Stewart wanted to be set up. So I helped him with that to line it up. This was used in conjunction with other radar arrays, but this one was situated just in front of the upstream of the drill tent. So this one will give a really high definition array of the surface channel below, well, where the drill site was. So this was a semi-permanent radar array. So at each position, it would take 21 measurements, and then you'd move it along a set amount and get a second measurement, and then that can be combined to get a 3D array. So if you look on the next slide, this is an action. So each step's 0.5 meter, and then you take the measurement there and move it along again. So the whole profile was 30 meters long, and I did an out and back profile. So that's 1,200 measurements. It's a pretty in-depth array. There's also, we nicknamed it the pirate array. It looks like a pirate ship. As well as that, this is some images of the profile radar. So this was towed behind one of the skidoos at approximately 5k an hour. It was close to as possible. And behind the skidoo, you'd have the receiving sled, which is the one on the right. And then behind that was the transmitting sled, which transmitted a pulse that was picked up by the receiving sled. So the whole profile was the whole skidoo setup was about 250 meters long, being towed at 5k an hour, and each profile is about 5 kilometers long. So it took quite a while to get this data. So this is the data I'm working with for my honours project this coming year, which will be cool. As part of the profile radar, it has super delicate antenna cables before and after the transmitter and receiver. Antenna cables are basically just ribbons of wire with resistors in series of increasing resistivity further from the source. These are super delicate, and we had to do quite a few in the field repairs in the evenings. So both Linda and myself got pretty good at soldering and fixing these up out there. So to sum up the surface geophysics, the whole range of methodology out there was basically just help constrain the shape of the meltwater channel at the Cab ice stream. And myself and Craig Stevens will be working with this data set over this year and coming years to try and just better model the shape of the stream before and after the borehole.
All right, so I'll talk a little bit about the sedimentology. So we were down at KISS2 for about 4 weeks. The first 2 of those for me was helping Sam with his radar profiling, mainly because we had to wait until the drill tent was fully put up and the boreholes were drilled. So due to some complications, we had the fantastic drill team had to drill another hole. So it took a little bit longer than expected until we could start coring, but when it happened, it was great. So what happened here was that we lowered our gravity core, which you can see in both of these pictures, down through about 504 meters of ice into the water cavity underneath it that was about 270 meters thick before we actually finally reached the seafloor. So this is fully blind work. We had no cameras down there, so we constantly had to monitor our rope length to make sure that we actually knew where we were in the water or the borehole. So how this works, just real quick, this gravity core is created for soft sediment, so any hard rock, it won't go through. And these are weights attached to it. So basically it is designed so that it just, once it hits the seafloor, it's heavy enough that it basically just sinks into it. Once the tension is released from the line here at the top, the valve over here closes, which creates a vacuum within the core tube, which theoretically allows you to pull it out without any issues. And then if you are successful with that, you end up with a situation like this, where as soon as it comes out of the ground, we put an end cap on the bottom to make sure the sediments don't accidentally fall out still. Then we detach it from the gravity core, we drain the headwater from the core, and then we saw the core tube to the right length, chuck another end cap on, and that's our core. So these were all of our attempts, and I won't go really into detail with this, but as you can see, we have tried a lot. It wasn't as easy as we thought, mainly because the seafloor is there's from the ice fin footage and the cameras that Niwa put down in the borehole, we saw that the seafloor is covered in big boulders that are draped by just some thin layer of sediments. So as I said before, we can't drill hard rock with our gravity core, so that was a bit of a complication, but nonetheless, we got 5 sediment cores, one of which was frozen and sent off to the University of Waikato to do some environmental DNA analysis on it. The other 4 are here at Vic, currently being CT scanned, and I'll be doing my thesis on that. So at this point, you could ask why do we bother looking at sediments underneath the ice shelf? Sediments are natural, they are a natural record of changes in the environment and climate over time, if you can date your core. So the environment and climate all have an influence on the sedimentation. So you can understand a lot about an environment from just looking at the sediments. Additionally to that, as I said, KISS2 is located at the mouth of a subglacial river channel. And currently under Antarctica, there's 400 lakes identified, or around 400 lakes identified, and these are all connected by rivers underneath the ice, basically. And because this is the first time we were looking at this, we want to know where did the sediment come from, how far from the inland Antarctica did they get sourced from? So could we understand how far sediments and water travels underneath the ice shelf? Yes or no? So that is really important. So then for me, for my thesis, the big questions to answer would be, what does a sub-ice shelf channel actually look like in terms of environment, ecosystem, sedimentation, all the work's physical aspects, like glaciation and all that kind of stuff. And yeah, what does the ecosystem look like, and what kind of ecosystems has it supported in the past? This is only successful if we can actually date our core, but we're going to give that a good try. Yeah.
And we both like to give a big thank you to the Antarctic Research Centre, Antarctic New Zealand, both our supervisors, Hugh and Gavin, as well as the School of Geography, Environment, Earth Science, and especially to everyone at camp as well.
Yeah, because it wouldn't have been such a successful field season without everyone's involvement and the 200% success rate for the drilling team. We are incredibly grateful to have been a part of this and to still be a part of this. So yeah, if there's any questions.
That's absolutely beautiful. You guys are going to be busy. Okay, no questions. You'll have to come back later if other people have questions, or we should just get through this. All right, Jamie.
Yeah, that's good.
That's
In here, man, what good stuff. This is tough act to follow. Let me find the damn button. Sweet. Well, good.
fantastic.
Sweet. Yeah, wow. Like I said, thanks everyone, and thanks yeah, all the previous speakers. Quite a tough act to follow. So but thanks for setting up a lot of stuff that I'll get into. Yeah, so hey, I'm really excited to kind of relive my cruise with you all tonight. I've just been off the boat for about 2 weeks now, and I'm kind of already awkwardly missing it, mostly missing the people, but also the cuisine. So this opportunity randomly popped up for me late last year, basically just with a short message from a friend, you know, asking if I could join this cruise to help with an airborne geophysics survey from a boat along the Amundsen Sea embayment. And being someone with absolutely no business doing such a thing, and pretty much the only person that said yes, I'm here to kind of give you a review of all that. And yeah, just kind of before going too far, you know, just want to give a big thanks to COPRI for supporting such an endeavor, UTIG, University of Texas Institute of Geophysics for supporting me, and the 70 new friends that I made aboard the research vessel Aron. Yeah, and I'd also like to just give kudos to kind of the New Zealand-based Antarcticans that have really paved the way for this increased collaboration with Korea and COPRI. This has been like a really mutually beneficial kind of thing, and I'm really grateful for those efforts. So yeah, so the talk of my title kind of lays it out there. This really was a full-on assault on the area, but really it's all about Thwaites. So I don't really have a lot of time. I'll do my best to kind of get an overview of our cruise, but really I'm just going to be scratching the surface of some of these topics that I'll bring up, and we'll miss some of the science that was done on board. So what's the motivation here? Basically, we've got one of Earth's largest glaciers is changing super rapidly and contributing to global sea level on human timescales. Like on, you know, we're thinking we're going to start seeing a big rise in like the next decade. So it's pretty amazing. It's a really popular glacier as well. So here, this one from New York Times. I think this is the only glacier that's been covered by the Rolling Stone. So they came up with this really catchy name, and while it is pretty kind of buzzworthy, that popularity kind of allows this really huge chunk of ice at the bottom of the planet be widely discussed. And I think that's a really good thing. And yeah, so why are we here? Basically, we're trying to forecast sea level rise. And to do this properly, we need models, and models need observation. yeah, the clock is ticking. So the fuse is blown. So Rolling Stone hits it again with some buzzy stuff. So how do we aim to kind of do this? Well, it's through, kind of another, assault type word, invasion. So this has been called the Thwaites invasion. It's a massive kind of UK-US led, but with partners from Germany, Korea, and Sweden, as well as a whole bunch of others. $20+ million all out, top to bottom, best we can do effort to kind of understand what's going on in the past and present to then better forecast what will happen in our shared future. So through this kind of innovative and collaborative international team, the kind of ITGC has really brought together leaders in understanding the key processes that are driving this change, some of that historical context, and then feeding that all to the kind of modeling community that then offers up products for policymakers and folks that are in the working groups from the IPCC, the Intergovernmental Panel on Climate Change. So you can see this is kind of what an assault might look like. So there's the Thwaites Glacier here. We've got folks arriving from land. We've got folks arriving from sea, operations all over the place. So yeah, I can't kind of, do that anymore. So yeah, just a schematic of kind of the Thwaites Glacier and the surrounding area. The whole idea here is that the whole kind of problem is that the relatively warm and salty water is creeping up on land. So it's going up over these kind of ridges, finding its way underneath the floating parts of the ice, and then attacking the grounding line here. And that kind of is creating an instability where the grounding line is resting on some bedrock we'll take a look at later, really, really deepens as you go further inland to the continent, creating a really kind of unstable situation. So that's kind of what we're kind of up to. So here's the route of the cruise that we took. We left Littleton. This part was terrible. And we got to the Kiwi Beak, kind of looks like Golden Bay a little bit, found our way around and then ultimately settled over here. But just for a bit of context, so the whole glacier system that we're looking at, the kind of aerial extent of this glacier is kind of outlined in red here. And if we look at the flow speed, so this area is kind of flowing quite rapidly into the Amundsen Sea. And then if we look at the bedrock, we really see the major problem here. So a lot of deep bed shape in this area here. So this is really creating an unstable position as the grounding line is kind of moving back from that. So yeah, so that's kind of, I'm going to zoom in to the Kiwi Beak and then its talons to get a closer look at kind of where we went. So starting out with this image here, and then just a kind of nominal look at breaking sea ice. So we started coming in up top here. This is kind of reminiscent of Golden Bay here. So we got the Kiwi Beak over here. Reach this point and basically, turn around, not getting any further. All this is basically chalked in full of sea ice. So we popped around the other end, tried to get around this city-sized iceberg, couldn't, landed here, couldn't go any further. Okay, cool, that's it. Shut it all down, hung out there. And then we did some oceanography around the area as well. So this is just a different look at that, but to really highlight that kind of variation in sea ice, but also just how bloody thick it was. So this iceberg here is about 80K long. It sat there for about 10 years. We actually put some sensors on it this year. It's really starting to move a lot. So some interesting things going on there. But yeah, so we posted up here, and then we had a friend around as well, the Nathaniel B. Palmer, the U.S. icebreaker, and the news got out pretty quick. Actually, we were on the boat when this happened. So giant iceberg blocks scientists studying Doomsday Glacier, and while most of that was true, we both ships actually have a heliport, but we were using ours. So we had 2 helicopters stuck in this little helicopter hangar here, which really enabled us to kind of get a wider reach into the Thwaites Glacier area, even though we still couldn't get there. So here it all is in one slide. So 27 days of science fun. Every day basically was just buzzy first thing in the morning. What are we going to do? Oh, weather's bad. Okay, we'll go do this. Weather's good. Okay, we'll go do that. So out of 27 days, we had 18 where we got to fly helicopters. We got to put in this amazing hot water drill camp on the Dotson ice shelf, not the original target, but did it anyways. My team flew 3,000 kilometers of ice penetrating radar over the Thwaites and the Dotson. So that's us in the pink lines here. We tagged 15 seals with oceanography sensors, CTDs. So that's them swimming around here in blue. We recovered some land stations and installed some land stations. So the AP-RES measures how fast things are melting underneath floating ice. And the GPS arrays kind of measure how fast things are moving, whether that's ice or continent. We installed a couple of tilt meters, chucked a bunch of things out of helicopters that gave us some more information on oceanography. So many CTDs from the ship, I can't even, we were always doing that. The paleo team picked up 8 sediment cores, and yours truly managed to chuck 30 rocks into his bag. So I'll first kind of break this down into 2 camps. So we had the Dotson, which we also called near Thwaites. And there we did the hot water drill, we did some radar and some land stations. Of course, there was a lot more going on, but I'm just going to highlight these ones. So with the little change in focus, we were going to have the hot water drill go to Thwaites. Didn't really have a backup site, so some quick action and some previous work in the area kind of highlighted this inflow of quite warm water through this deep trough into the underside of the Dotson ice shelf. And so we figured, hey, let's go to the deepest part there, right kind of where the inflow is. So that kind of set that up, and basically the whole kind of question is how much heat is getting delivered to this underside of this ice shelf. So there's the camp, all put in by helicopter sling load, 50 helicopter sling loads. That was all done in one day. Really, really incredible what you can do with a helicopter from a ship. So they managed to get a 400-meter hole, did some amazing oceanography with that, with the CTDs, as well as some induction moorings from the group led by David Holland and Claire Ayers at New York University. Bass has got some sediment where they sampled underneath there. James Smith is going to be cracking into that soon. Yeah, so the University of Texas Institute of Geophysics, this is our radar system. So in the 2 booms hanging off to the side, the right and left, those are radar antenna. And then the one up front here has a magnetometer right in the end of it. So we're able to kind of do some geology focused geophysics, as well as some sensing beneath the ice. And yeah, basically there's some other sensors in there as well. We've got a laser altimeter and a camera pointing down, taking some really, really amazing images as we fly over. And then yeah, kind of it would be really great if the helicopter did not return. That meant they were off and we could get some sleep for a minute. But yeah, the real brain of the radar systems, this guy here, Lucas. So Lucas is not only a kind of an amazing friend, but a really great leader, and was really, really big hoot to work with. He's a really talented musician as well. So here he's promoting his band, the Old Dusties, back there. But anyways, the real brain of this system is this fragile, crazy system of instruments. The brain coming in here, feeding in all the sensors that we've got on board. Yeah, so it's incredibly fun to set up, and is pretty much as fragile as it looks. So too many details and fun stories to get in here, but yeah, really incredible kind of system. So around the Dotson ice shelf, we looked at a fern density survey, and this was based on some previous work around Thwaites Glacier, where radar was flown around the same time that a fern core was collected. And so we thought we could do something similar, but we had the added bonus that we had another calibration site where we saw blue ice around the area. So the little survey just in here around the camp and then up over to some of the blue ice kind of allowed us to do that. And another Dotson science objective was kind of looking at this amazing sub ice shelf basal channel and the evolution of it. So if we look at some cross lines along here going from the grounding line to the ice shelf front, you can see that at the base of the ice shelf here, that's this kind of real bright return here. You can really see two nice channels here. And then you can start to see two, maybe they're coming a little closer and then they're quite wide and broad. So you're really seeing this evolution of this channel as it makes its way out to sea. So that together with the CTD data just offshore really makes for a really complete, cool study. So we also got up on land. So this is a site, Jeffrey Head. A lot of stuff has been done around this area. So about 10 years ago, Polnet, a US program, installed a seismometer and a continuously operated GPS site just around here. There's a weather station there and some other folks have gone around and picked up rocks in the area. So let's see what we can find there. So yeah, we basically, the job here was to get this site back up and running. So it was, hadn't been visited for about 2 years. And yeah, so we kind of nursed it back to health. So this is as installed 10 years ago. And this is kind of what it looked like when we turned up. Spot the difference. There's a missing wind generator. There's a missing meteorology sensor on the other side of this. There's a broken wind generator and the satellite links are not pointing up. So we fixed those. We installed a new receiver and a GPS antenna over here and all good back on top. And this is one of the fastest moving chunks of Antarctica out there. And yeah, so we recovered some data and got it back up and working as well. So, and of course, while no site visit to rocks is complete without picking a few up. So here we found, kind of the remnants of the last great ice sheet that covered this area. And this is a beautiful kind of glacial erratic that found its way into my pack and will be in the laboratory soon. And then from the very top there, Jeffrey Head, we'd see this amazingly glacially polished, these lines here indicating which direction the ice was flowing, parallel to the ice shelf today. So some really cool rocks to pick up there as well. So if we pop over to the Thwaites, I'll talk about some ocean deployables, and then we'll get back to the radar and land station. So this was just absolutely amazing to me. So Jamin Greenbaum at Scripps and David Holland at NYU just having a riff session on how to deploy these things. Basically, you chuck the CTD out of the ship, it starts measuring and it sends the information back via radio. It's absolutely amazing and really cool to watch these guys work. So Jamin had a really great season, deployed a bunch of sensors all through this kind of area where there's this really complex kind of inflow of warm salty water and then this outflow of glacial melt where we're seeing the highest melt rates in the area, up to 100 meters a year here. This is unbelievable. So to have in situ data there is really, really special. We had some other help deploying CTDs, that's oceanography sensors. So the SEALs were really willing to help this year as well. So basically pop out there and frighten a seal for about 10 minutes, a bit of glue. It's the sensor is put on their head and it is not attached to their skin. So they shed it after about 6 months or so. And man, look at them swimming around and sending a whole bunch of data back. So here, the folks that were installing these are a mix of marine biologists as well as oceanographers. So the top plot here gives an idea of how far they're diving, what kind of head movements they're making. So they're classifying this as like hauling out versus just hanging out. And then they also carry some pretty sensitive temperature and conductivity measurements on their heads as well. back to the radar team. So 2 years ago, the radar team picked up the blue lines, and this year we flew the red. So just connecting up quite strongly with previous seasons. And this blue here is kind of a modeled channel based on topography as well as some surface features in the ice sheet. And so what we're really trying to do is get an idea of how that is emptying into the really fast melting portions of the ice shelf. And so here's just one example of a radargram. So the top is kind of along here. That's the upper ice surface. The bed is just along here. All this noise is coming from the kind of intense crevassing. That's all of this is grounded ice. So all of this is just kind of related to the intense kind of crevassing associated with that rapid speed. And once things slow down and chill out a little bit, you can really start to image some of the laminations here. But for us, the most important thing are to see these bright spots. Now, these bright spots are actually wet spots. So up here on the map and along this line here, we cross over quite a few mapped subglacial lakes as well as small channel systems. So it'll take a lot more to kind of understand, correlate these with some of the other lines and some of the other data going into this, but it looks like we've tagged some subglacial wet spots of sorts. So pretty exciting stuff there. And then of course, back on land here at Mount Murphy, this is a large volcano kind of just kind of near the Thwaites Glacier there. And interestingly enough, this is basically the first instrumentation at this site and basically the first time anybody's stepped foot here. So we left this for science. This is a continuously operated GPS system and the first ever deployed by COPRI. So a huge success there. And of course, while we're there, I couldn't help myself. Amazing glacial striae, great glacial polish. This is parallel to the Thwaites Glacier. So we're really picking up paleo Thwaites there, and some beautiful glacial erratics made their way into my pack. So all up, there's a lot of numbers here. We got a lot of prep going into all this, and then a lot of waiting and all that stuff. But it all adds up to pretty amazing stuff for me. So yeah, thanks again for your guys' attention, and happy to answer any questions. Hopefully more on this too, because there's a lot we're missing. This is a whole season lined up in 27 days, a whole national program. So really hard, but just trying to hit the high notes. So, thanks, guys.
Absolutely beautiful. Yeah, that's insane. quite a lot covered there, Jamie.
Yeah, sorry for that. It's really difficult because I could just go right into my rocks, but there's just way too much cool stuff out there. So yeah.
Yeah, no, it's really lovely to see this kind of broader picture of what other people are up to, rather than I guess just the things that we do here in New Zealand. Awesome. So do we have any questions on the last 3 talks? Did have a note from Tim just applauding the successful field season, in case anybody missed that. 200%. I'm not sure I can remember everything that happened, but yeah, if nobody has anything to say, I'll wrap up and thank all of our speakers. It was, that was great. I think, as I said, there's still quite a lot of stuff that we didn't cover tonight, and it's always great to see what has happened and get these little tidbits, just as everybody's fresh off the ice. So thank you very much, and this will be available up on YouTube in perhaps a couple of weeks.
I might just add a little plug for the society. We're always kind of welcoming new members, and come on in and join us. We've got a couple events on this year, and always kind of fun stuff on. So and we kind of interact strongly with some other branches around the country and some of the other institutes as well. So anybody interested in this stuff, just join up.
yeah, you know who to speak to, Stefan, Jamie, Natalie, depending where you're from. Or reply to my emails. Thanks, everyone. I'm gonna just stop recording.